time to start seeing if we can beat the betting firms using just linear models. Okay, and this data set that we'll be using here is football probs.csv, and here's what it looks like. Contains 2 rows per match, one for the home team, one for the away team, and we have all these wonderful implied probabilities that the different betting firms are using. You can see what I'm doing here. I'm just converting the date to date time rather than a string, and these variables are converted to categorical variables, which just means that this variable here, actually what is in the underlying data set, if we type values, we get the strings out. Or do we get strings out? No, we get a categorical array, which is an array that underneath has just various values 0, 1, 2, and so on, but then knows that all of these different labels are applied to the underlying values. But it also helps us a great deal when we'll be doing the our regressions. Right. Let's have a quick look at something from the data, which is the goal difference between the two teams, split by whether or not it is the home team. And this is one thing that's well known in by people who are excited about football, is that there's a tendency for teams that are home to score more points. And that's something that is immediately clear. So if we just do a group by home and take the goal difference and compute the mean in these groups, whoops, this isn't a function. Here we go. We can see that the goal difference is 3.8. If you're getting 0.38 goals more on average if you're the away team. That's one of the things that we'll be looking into here. And let's create our outcome variable as well, so that we have that. Plotted as a bar, losses, wins, and draws. Great. Okay. Odds to probabilities, we've already looked at that. And that gets done underneath. And we have some convenient variables here that we can use later on. Here again are some of the betting probabilities. So we can see for matches where the firm won, bet 365 on average had an implied probability of 52% of that happening. And again, these are plotting some of the probabilities. All right. So one thing that we can meaningfully ask is we're going to try and see if we can beat the betting firms. And one natural question that we might ask is whether there's more information in the average implied probability. So if we take calls here win, these are the probabilities assigned by the here we have 6 different betting firms. So here are the probabilities that each of them are assigning. So as you can see, they're not too far from each other, but there's some dispersion. For this first match, for instance, and let's just add the team names. And let's take a sample of 5 random rows. So here with Parma versus Lazio, we can see that the bet 365 assigned a probability of 37.5% to a win going to Parma, whereas LB assigned 35. So it looks like we have from 34.6% to 37.5% probability. So there's some difference here. They do disagree. And one natural way of thinking about it is that each of these different firms are receiving a signal of the true probability, and then they receive a noisy signal. And if that's the case, then given that we have access to all of these probabilities, we can compute a more informed guess, namely the average probability. And so we can do that by just looking at the win rates here, and then we can take the mean over, and we want to take it across, not down, so we take x equals 1. And that's the average probability for the first row, 51.4%. That makes sense, right? It's there between 40 and 47% is the minimum, and 43.9 is the maximum. All right, and we add that to the list of win rate probabilities here. And so now let's make a plot here where we do histograms of 3 different win rate probabilities. Oh, we didn't create it yet. There we go. So here we can see that that the 3 firms are actually they're rather in agreement. The 2 firms are rather in agreement here, and our average prediction is also in the middle. So actually the overall distribution of the predictions are fairly close. But of course it might be that for any given, the question is whether there's any given group of matches where the win rates were closer. So for instance, what we could do is we could say, let's take all of the rows where we're looking at the winning team, and let's take all of our columns with the win rate probabilities. They're here. So these are all rows for a match where the team in question won. And we can ask, what is the average value? And now I mean average down, because I want to see, so I want over x is 0. And that's going to give me the average win rate probabilities assigned in cases where the match was actually won. And what we can see is that actually it looks like Bet365 performs rather nicely for those matches. They're assigning an average probability of 51% to a win, whereas we do have this IW platform which only assigns 47% win rate probability. Of course, it might be that they're not there can be many reasons for this. For instance, they might be missing for different rows, so this mean could be computed for different values. So let's just make sure that starting by dropping any row that has missing in just at least if it has missing in any columns, and that didn't really change it. So as we can see, our average win rate for the matches that were in fact won is at least performing worse than Bet365, but it's better than IW. So what this is indicating is that might be that there's actually some heterogeneity in their abilities. But a better way of thinking about this is to compute some measure of the goodness of fit. And one measure is the root mean squared error. So the square root of the average of squared errors between the true outcome, which is 1 if the match a dummy for winning, and our predicted probability. We can compute that for many different measures. So for instance, here we have it computed. So these are the squared errors, and then it returns the square root of the average of those. So we could take the difference between d dot and then the average probability of winning between that and the winning probability, and that has a root mean squared error of 0.44. Or we can do the same thing with Bet365, and let's see, 0.443 and 0.4429. So Bet364 appears to have a lower mean squared error. So in that sense, it's doing a better job of fitting the data. And here's a function that that just computes that root mean squared error for all of the columns in the data set, and we're aggregating them and then just plotting it in a bar chart. And so what we can see is that, yeah, Bet364 and VC appear to be doing rather well, and as expected, these two, IW and LB, aren't doing as well in terms of predicting the odds. Okay, but let's now turn to a linear probability model of the winning probability. So a linear probability model of the outcome that the team wins the match. All right, so just to illustrate, let's start by showing how to use NumPy. All right, so first off, here's a small point on the home dummy. We need it to be a float. So the data type of home here is true or false. It's a Boolean, and it turns out that NumPy does not at all like it. So if we try to work with that directly, we're going to get an annoying error here, which actually is not at all informative for what's happening. No loop matching specified signature casting. Yeah, but trust me, you want to convert your dummies to either floats or at least integers. So we create a float, which is home underscore, and then we use that variable instead. All right, so let's see what I'm doing here. First, I'm creating I, which is a 51,000 array, which is the same size as our data set. And I is true and false all the way down, so that when we go D of I, what we're getting out here is a smaller array where we are dropping the rows where any of these columns, home, win, or the probability of winning columns, they have to all be not null, so non-missings, and all over the first axis. So that is, for each row, they have to all be non-missings. And then when we subset our data set, I use d.log to locate I along the rows, and for the columns in my X matrix, I want a dummy for being on home turf, and then I want the predicted win rate probabilities, and then my win rate dummy here. Okay, as my outcome, and I'm going to reshape that so that it's a two-dimensional vector. What does that mean? Well, let's run this and then go y.shape, and it's 44,000 by 1, as opposed to 44,000 and then no second dimension. And then we're ready to use our good old OLS formula, x prime x inverse x prime y. So we take the inverse of x prime x and we multiply that with x prime y. And that gives us beta hat, which is a numpy array, and we could flatten it, so make it one-dimensional, and then put it into a pandas data frame where we tell it what to write on the in the index column out here, namely the same order of the variables that we were giving it. And so we can see that we're estimating a positive coefficient on the home dummy, but this is actually, so if we were to run the same regression, oops, we're forgetting to put in a column of ones actually. Let's give it a constant as well, then we can see how this is done. We want a column of ones, so it should be n by 1. And what is n? Well, n is however many rows we're selecting with this indicator variable. So this is our column of ones, and let's add it to x. We stack it horizontally like so, and just overwrite x. So now we also have a column of ones, and we have to also tell it here when we're printing it that we've added a constant term. Here we go. Okay, but as you can see, the home dummy is rather low. That's pretty interesting. So one thing that we could do is we could try to delete some of our explanatory variables, all the predicted win rate probabilities, and re-estimate. Of course it doesn't. Now we have fewer variables, and here you can see we're getting a larger home dummy. So what's that telling us? Well, it's telling us that part of it is that the bookmakers have already built into their expectation models here in the predicted win rate probabilities part of the effect of the home field advantage. But as you can see, there's still a 0.04 coefficient on home. I'm not showing standard errors here, but that implies that there's a 4 percentage points greater probability. Some interesting things to note here. One is that we're attaching a lot of weight to the Bet365 win rate probability and a lot to VC, and and that's pretty interesting because those are actually the two firms that have the lowest root mean squared error. So that makes quite a lot of sense. There's a lot of precision in their numbers, and then we're actually attaching a negative value to LB. And as you can see, LB is tall here. So of course, LB on average is doing relatively okay, but this is telling us that our model takes a linear combination that puts weight on these two, a lot of weights on these two, and then actually goes in the opposite direction of what LB is saying. Quite the diss. And you can also see that we're supposed to move away from the average here in our linear combination. So if you wanted to use this to do betting, what you would do is you would collect the implied probabilities from all of the betting firms, and then you would start by 9.6%, then add 4 percentage points if it's a home match. Then you would take 0.51 times whatever probability Bet365 is giving, 0.014 times what BW is giving. Then you would subtract 0.01 times what IW is assigning as probability, and further subtract 0.43 of what LB is assigning, and so on. And that would give you your best prediction of what the probability of winning is. All right, so I'm going to switch now to using stats models, which is kind of cheating, but does things a lot faster. So in stats models, we write our model as a string win equal to, and then all of our covariates here. So here we're doing the same thing. Oops, we're not actually using team fixed effects here now. All right, and then what we can do is we can do a prediction y hat, and we can enter that into our data frame. So now we have our fitted values, which we can also up here compute as just beta hat x times beta hat. That's also just our predicted values from the regression. And then we put it in y hat in nicely. All right, let's first plot our estimates. Here they are again. Visually, you can see that most of the positive weight is on Bet364 and VC, and the negative weight on LB. All right, and then let's plot the out of sample fit of the model. So one of the things that we did here, and one of the reasons why the parameter estimates are different, is that we're not giving it the full data set to estimate on. We're estimating it on, or rather we shouldn't be, at least. We should be estimating only on the training data. And the training data is going to be the data set that where we have no missings and where the date is before 2015, 1st of January. There we go. Okay, we can see that changed results a little bit. Okay, so this is estimating our parameters on only the part of our sample that goes up to and including 2014. And then what we're going to do is we're going to evaluate how well our model is doing on a holdout sample, namely the remaining part of the data set, the part that lies after 1st of January 2015. All right, so and what the fitted variable that we created, we call it AMN probability of winning. Maybe we should have called it y hat probability of winning. indulge me. Right, so let's look at matches that were won, that occurred on home territory, and where we are in the holdout sample. And what we can see here is that our new model out here is predicting a higher probability for those matches that were in fact won than any of the betting firms did. So our model, even though it was estimated on a sample before 2015, is performing better out of sample than what the betting firms are doing, at least than what the implied probabilities. And let's look at away matches, and here we can see that for away matches we're still the best, but not by a whole lot. So we're not doing much better than VC or V365, and this is, again, we're evaluating what is the probability of winning for matches that were in fact won. But that's not doing anything with all of the matches that were lost. So for those, we can again turn to the root mean squared error. And here we see that we're doing very well, but VC is almost doing as well as we are. Probably explaining why we're attaching so much weight in our estimated model to the VC probabilities. Okay, but let's see if we can do even better. So one thing that we can do up here very easily in stats models is we can add a team fixed effect. So now let's estimate the same model but with team fixed effects. This takes a little bit longer because we're getting a much larger set of coefficients. So if we take our stats models regression fitted object and ask it to print a summary of everything, we can see that now there are a lot of coefficients, such as coefficient on Everton, which is 0.035, and again interpreted as percentage points probability of winning relative to whatever the omitted team category is. All right, so we've estimated a rather large vector of parameters. In fact, it's 304 parameters that we're estimating, and we have 36,000 observations of team matches, so that should be fine. And we can see that the loadings are still along the same lines. Okay, so let's see what our predicted probabilities. Now we're looks like we're a lot higher than we were before, and even though we haven't improved all that much here for the away matches, for root mean squared error, it moved in the wrong direction. So that's pretty interesting. So now it looks like our model is getting a higher mean squared error than any of the bookmakers. So how can that happen? Well, we could try to see how our root mean squared errors looks if we evaluate the mean squared error in the training sample. And here we can see that our model is getting a much better fit, but in the holdout sample, not so much. So this is an example where we've added many more variables. We have 304, and what we're doing is actually resulting in a poorer model fit out of sample. So we're probably overfitting the performance of some of those teams in our training sample in a way that did not match up to what happened after 2015. All right. And to just wrap things up, this was all work done where we were modeling the probability of winning. However, what happens for the matches that were not won? Well, we're just looking at the root mean squared error of winning versus not winning, but there's also a lose and a draw, and it's not as if this model tells us how to assign that remaining probability. So if we look at let's look at what our model is, and let's compare it to Bet365. So here, for instance, KRC Jenk versus Beershot, our model is predicting a higher probability of winning. But what about those other outcomes? So losing and draw. How should we assign the remaining probability? This linear model that we've developed does not tell us how to distribute the 1 minus 57% across these two outcomes. We could do a separate linear model for loss and a separate one for draw, but there's no guarantee that those probabilities would sum up to 100%. And if we rescale them, then we're no longer doing as good of a job as fitting the individual outcome. So if we were to formulate one for win and one for draw and one for loss, and then we divide them by the sum of those three, well, then we're taking this number away from what it was fitted to be and where it performs well. So the linear model isn't really doesn't have any good extension for dealing with these three outcomes and the fact that they're related and that the predicted probabilities have to sum to 1. So that is what Logit model will help us with.